Good afternoon, everyone. So we'll start the afternoon session today. So I just want to remind everyone, just please use the microphones if you want to ask a question. There's pretty much a microphone on every row. So whoever has the microphone, please pass it so that people can use it. So the first speaker is Anil Shaji from Trivandrum, right? And he'll talk about simulating the trajectory of a mixed state quantum computer.
Okay. Good afternoon, everyone, and thank you, Abhishek, and thank you to the organizers for having me here for this workshop. Unfortunately, I'm able to spend only a few days here due to other commitments, but so far it has been, or at least one session has been thoroughly enjoyable. So, this is not really a talk about trajectories per se, that I should say in the beginning, but I feel that or believe that this discussion that I'm going to have may quite benefit from some insights from people who do work extensively on trajectories. Even though I do work on open systems quite a bit, I'm not familiar with the details of how to use trajectories to get these calculations done. So this is a work that I did with two of my students, Shalin Jose and Akshay Sairam. We had recently posted the work online. I'll give the reference later as we go along. So the key question that is being discussed is what is the main resource that allows mixed state quantum computers to perform certain computational tasks exponentially faster than the best known classical algorithm. So that's a question that one is after, right? So that's a question that I've been bothered about for a while now for various reasons. And it brings together two of my interests. One is being a mixed state, there is an element of open quantum systems in it. And there is also the notion of correlations other than entanglement in quantum systems. These are two topics that are something that I'm very much interested in. So this question brings these two things together. So, right. So what, just as a background, what is known about resources? There's a lot of interest in quantum resources in the last decade or so. But as far as computation goes, the definitive statement that is there goes back all the way to 2003 when Jose and Linden worked out the resource for a what is the key resource for exponential speed up in a quantum computer that uses pure states is essentially entanglement that grows unboundedly with problem size. And the way they show this is to show that if it did not grow unboundedly with the size of the computation or with the problem size, then there is a classical computer that can efficiently simulate the quantum one. Therefore, the quantum one is no better than the classical one. So that's the rationale. In the same paper, they also remarked that basically we cannot make any statement about quantum algorithms or quantum computers that work with mixed quantum states. Why, if at all, it should give a computational advantage over classical one. So of course the first question is, does that actually happen? Is there a mixed state quantum computer that gives you some kind of advantage over a classical, best known classical algorithm, even if it's a toy model? So that question was sort of addressed. It came about from essentially inspired from experiments on NMR based quantum computers long time back. It came essentially through this paper by Anil and Laflamme, who introduced this interesting sort of workhorse model for mixed state quantum computer, which is called the DQC1 model for quantum computation. So here they called it the power of 1 qubit model of quantum computation. So what does it do? What it does is that in the end, this is a means of figuring out the trace of this unitary that is acting on a completely mixed state. And the only additional ingredient or the so-called quantum ingredient that goes in there is one pure qubit to which the unitary is coupled to. It's a controlled unitary based on that one pure qubit. And later work also showed that that qubit here, which is called the top qubit, need not be fully pure. It can have a little bit of purity and it still does the job, okay, with a certain polynomial overhead in the computational cost. So ultimately what it does is that you run this circuit multiple times, and each time you measure essentially the top qubit either in the x basis or the y basis. And the expectation value of the sigma x and sigma y operators, one can show with a little bit of algebra that it is proportional to the trace of real and imaginary parts of the trace of un. So this is the DQC1 model, which has endured quite a while. People even now nowadays even talk about DQC1 complexity class and so on. Right, so that is a very simple idea. Well, what does it do? It calculates the trace. Is it of any use? Probably not, but it does it. And the point is that this is a n qubit unitary. So as a matrix, this is 2 to the n by 2 to the n. So if you just want to compute the trace by adding up the diagonal elements, you have to add up to 2 raised to n elements. So therefore, by definition, it is, if you try that approach for a classical solution, that is not doable. You simply cannot add up these elements because there are an exponential number of them. So your cost of adding it is exponential in small n. So anything that's exponential in small n is considered inefficient as far as a simulation goes. Here the point is that you never actually look at this unitary or these qubits. For all that matter, it's in a completely mixed state. Therefore, if you get rid of this part, the unitary actually has no effect on it in a sense, because a unitary acting on a fully mixed state, it essentially can leave it completely mixed. So it can have absolutely no effect, but it's still, what one does here is that you're measuring the top qubit and you have to do it a fixed number of times, independent of n, in order to get these numbers to a desired accuracy, whatever that is. Right? That's the only point here. And one can show that if you consider this natural division of this system into two halves, there is no entanglement built up between these two parts. If you cut it here, you'll find some entanglement, but again quantifying it, catching it, etc. is quite hard. And once you make these top qubit not pure, but make it mixed, this entanglement, whatever is residual, goes down very fast, into the sense that is not there. So entanglement is not the reason, probably not the reason why this particular setup works. So with that, an interesting question which I thought I would pose here, for which there is no definite answer, but we do have some partial answer, is something that was talked about, mentioned earlier also. When you have a mixed state of these n qubits, you can consider them to be really part of a larger Hilbert space with another n qubits or more than n qubits. And the question is, in some sense, through this circuit, are you getting entanglement between all of this, or in some very vague sense or very hand-wavy statement, which I have no real hard support for, one can ask the question, is the mixed state quantum computer essentially sort of sucking in the computational resources of this larger Hilbert space to make this computation possible, right? So that's a intriguing question, but for which there is no clear answer. But we have done some work in that direction. That's not really the story that I want to tell here. I'll just mention that. But let's actually look at it a little carefully, which is to say that I can always consider a purification of this mixed state into something that looks like this, where I have chosen the particular basis in which I have written the original mixed state to be the eigenstates of the unitary U. Okay, because it's a fully mixed state, I can simply write it as uj with equal weights, and that's just as well a good description of this, right? So if I purify that state using another n qubits, also in the same state, I will get a state like this. And you can easily see that if I trace out E out of this, I will get back the fully mixed state written in the UJ basis instead of the computational basis, but big difference because it's really the fully mixed state. And then I can see what the unitary does, because in this way it's easy to calculate what it does. And what it does is that it creates a state like this, which is now an entangled state of this top qubit with the 2n other qubits that I have considered. So that's that state. And if I trace out that system that I used for purifying, then I get a state of the system that looks like this after the action of this unitary. Where what I find is that each of the to each orthogonal state of the qubits in the bottom register, I have associated a state of the top qubit. Now these states that I have associated with each of these orthogonal states is not themselves mutually orthogonal. They cannot be, because it's a single qubit and there are only two mutually orthogonal states. So these guys are not orthogonal to each other. So this led us a long time back to compute whether there is any non-classical correlation that exists between the two qubits, as quantified by one of the favorite measures, which is quantum discord. This is which is essentially defined as the difference between the total correlations minus the classical correlation. So what is left behind is essentially the quantum correlation. I'm not going into how to define it and what it means here, but that's just a measure of non-classical correlations other than entanglement between the top qubit and the rest. There was no entanglement between the top and the rest. So is it something else there? This is again fairly old historical stuff. And we computed that for the DQC1 model and could find that irrespective of the purity of the top qubit, quantum discord is always there between the two. And this is a comparison with entanglement, not across the top qubit and the rest, but entanglement across any possible division of the n+1 qubits. You find that with the purity of the top qubit, one of the measures of entanglement will abruptly drop to 0. So what one finds is that these kind of non-classical correlations is probably it's there, and it's probably a better measure for the quantification for the resource that is actually goes into the that enables this particular system to do better than classical counterpart. So that is just a conjecture. But then while this was being discussed, there was this other paper that came out in 2010. It says that what about unitaries that do not create discord between the top and the bottom? Okay. Is it possible that such unitaries, the trace of those unitaries can be found efficiently using classical means? The obvious answer is no. If you look at the problem, it is again a unitary that has 2 to the n entries. You're not going to find the trace very efficiently or easily. So the question is, so what about those cases? In that case, you have explicitly shown that there is no non-classical correlations as quantified by discord, or any of the other measures you can compute. There's nothing significant there. Then does that mean that non-classical correlations are not a good idea? It's not the resource that goes into that you cannot consider. Is it that you cannot consider it as a resource for mixed state quantum computation? So that was a little bit disappointing and bugging because it said that we have to look harder or somewhere else. So, and there was no real other obvious candidate for it. Okay. So, well, then you can do two things. One is that you can go look for some other thing, or you can say that, okay, maybe this particular case needs a little bit attention, and if you really work on it, maybe you can show that the particular case where there is no discord is actually simulatable classically efficiently. So that will address this particular deficiency, because what you are saying is that, yes, in this case, there is no discord, but then you are also saying that no, in that case, it is efficiently simulatable classically. So what I want to talk about is a little bit here, what I want to talk about here is whatever is our effort to go in that direction. I wouldn't say that the answer is complete, because there are assumptions that go into whatever results that we obtain. So there is scope for more things to do, right? So before I proceed further, it's interesting to note that what this whole circuit essentially does is that the completely mixed state that's sitting at the bottom n qubits essentially is able to sample from a uniform distribution over 2 to the n elements in an efficient way. It allows you a means of doing a sampling, which otherwise requires, if you do it classically, it will require 2 to the n samples. but it allows you to do that efficiently. Just the presence of this completely mixed state, which appears to be benign and not doing anything. Okay, and the ability to do that is essentially translated, or it is converted into something that is actionable by the presence of this non-classical correlation between the bottom register and the top register. So once that non-classical correlations are built up, then you can take advantage of this ability of this state to sample efficiently from this 2 to the n elements that is uniformly distributed by essentially measuring the top qubit only. Okay. So that's one way of looking at how this particular circuit seems to work. So there were some work in this direction. For example, Brian Easton in a archive paper, which I believe never really got published, I'm not really sure. I have not found it, at least, showed that if you have what are called concordant computations, which is that the discord between any two pairs of qubits in this entire n plus 1 qubit is always 0, then it can be efficiently simulated. But that's not the case we are looking at, because we are only looking at the top qubit versus the rest. And then similar results were also obtained by Cable and Brown back in 2015. So I've given those references there. And we have also looked at, as I had mentioned earlier, this question about what is the connection between the quantum discord between the top qubit and the rest, and the entanglement in a larger, hypothetical larger Hilbert space that the mixed qubit is part of. So those results are there in these two papers. One is published, and this is in the archive. This is with another couple of students of mine. So there seems to be a connection there also. So that is what sort of prompts me to consider the fact that this system may indeed be simulatable. Of course, the path to try and construct the simulation seems to be quite hard, which is part of the reason why I thought I'll talk about this in a forum where there are people working on quantum trajectories sitting, because that approach may yield a better and easier direction in or way of doing this, right? So let me try to make that a little bit more clear. Okay. So let's look at the particular problem, which is that what is the condition for the unitary to create zero discord, and that is in that 2010 paper I mentioned. So they obtained this condition, which says that the dagger of the unitary should be proportional to the unitary. Since it's a unitary operator, then it has to have this form. So un is some phase times a fixed phase times some operator who squares to the identity, which essentially means that this operator here can have only two possible eigenvalues, +1 and -1. So if you bring it to its diagonal basis, it has to be +1s and -1s only, because if you square it, it has to come back to the identity matrix, apart from this overall phase which we set aside. Therefore, in this particular case, actually, what you are trying to compute, the trace of u, which is essentially the trace of O apart from a factor of e to the I5, which we will talk about separately, is simply the difference between number of +1 eigenvalues and number of -1 eigenvalues. That's what you're trying to compute here. That's what the DQ-Siemens circuit is actually giving. So since in the following discussion, the order in which these eigenvalues appear do not matter much, we will worry about it where it matters as we come to it. One can always assume that you can write this O operator in this form, VD dagger V, where D is a diagonal matrix with a whole bunch of -1s and a whole bunch of +1s. The idea is to figure out how many -1s and how many +1s are there. Of course, you can always think that you can just count it, but you cannot, because this is a 2 to the n by 2 to the n matrix. So if you try to count it, you are going to count 2 raised to n +1s and -1s. So that's not going to fly. So you have to figure it out without actually counting it, right? Without looking at it. So one of the things that one noticed is that in this, if you assume that this V is a hard distributed unitary, a random unitary matrix, then one can show that the expectation value of any diagonal element of that O should end up having a form that looks like this, which contains information about the trace. And more importantly, from a perspective of trajectories, is that if I send in a computational basis state into the unitary and ask the question, what is the probability I get the same state after the unitary is applied, and average it over a fixed number of such computational basis states, then I'll find that this expectation value also contains information about the number of +1 and -1 eigenvalues. So if this quantity, okay, which now we have departed from the mixed state because you're actually sending in a pure state into a unitary, evolving it, getting another pure state. So you have replaced it, the whole thing by a pure state evolution, but averaged over a few such pure state evolution, you are able to get a number, a quantity, which if you can estimate, which is say 0.6, for example, it will give you the number of plus and minus eigenvalues modulo an overall -1 because there is that e raised to I5 that we left out earlier. Okay, so that's observation number 1, right? Question is, if you can do this, right, then this, for this particular case, just by figuring out what the y value is, you can get the x value. Notice a few things about this graph, that this is for a real, a bunch of real random unitaries that we created. We computed this quantity numerically, and we find that it's very neatly follows this expression, and as n becomes large, this becomes better. The agreement is actually better when you have the number of ones and -1s close to being the same. When it goes to the edges, things get a little bit worse for reasons which we will mention briefly, right? So then we went ahead and said, okay, so this is now, there is a simplification in the kind of unitary. Can we actually try do a simulation of it brute force? Because we tried various other things. Now this is one of the methods that we found with a certain number of caveats, which I should mention very clearly, and there may be a better way, so that's yet to be done, but we believe it can be done. So, what are the assumptions? Assumptions have to be laid out very clearly so that you know what the boundaries of what I'm saying are, right? First is that the unitary U itself, we are assuming that it is efficiently implementable with a polynomial number of elementary quantum gates. If that's not true, the statement is that then the DQC1 circuit itself cannot be constructed, and if it cannot be constructed, you can use that method to find the trace. So then where is the question of comparing its performance with a classical computer, because you cannot build that quantum computer anyway, right? And these are things that I'm sure you know that even if you cannot do it exactly, you can do it approximately well to arbitrary accuracy with a finite number of gates, right? So some of the questions that we thought we were easy or should have been solved in the literature or should have been found, it turned out that it's not there, right? Is there a direct way of, so what do we want to do? We want to pick a unitary, a random unitary, which is ones and -1s along the diagonal with some V and V dagger on either side. Okay, so that eigenvalues are this. We want to numerically test out whatever you are trying to do. We want to construct such a unitary, break it up into elementary gates. Now that's, well, with the status of quantum computation these days, with everybody implementing various things, one would have thought that that problem would be at least sufficiently well addressed. But it turns out that's not really true. Actually, finding a suitable gate decomposition for a unitary with a diagonal unitary with only plus and -1 eigenvalues, forget the V and V dagger, that itself appears to be quite difficult. Not much literature on that matter, right? And even simpler, you can build such a unitary with multi-control sets, but finding a decomposition for that also seems to be rather not something that people have worked on except for 2 control, 3 control, that's about it, right? So which prompts me to kind of make the statement that this still seems to be a fairly open problem, and with the status of quantum computers, one would imagine that this is an important problem to really address systematically. But anyway, so let's press on ahead. We'll say that let's assume that U is made up of some set of universal gates, which we chose like this for certain reasons. Okay? We wrote down these gates, Hadamard's T and C naught, as exponentials of some of Hamiltonians acting for a certain fixed amount of time, so that these gates are applied. And let's assume that it is grouped into some layers, m plus 1 layers of mutually commuting sets. And for each layer, you can write an equation that looks like this, which is essentially the action of all the gates in that layer. They're mutually commuting, so the order within the layer doesn't matter. But once you multiply them up, the order matters because they are not each layer does not commute with each other. So this H is not such a nice object, because if you want to find it from all these component edges, which you can write down directly, you have to actually do the Baker-Campbell-Hausdorff kind of messy affairs. But one tried to do that anyway and found that you can indeed, for the examples that we were able to do, you can indeed construct that edge, and it converges to the right edge that we are looking for. And the fact that O is an involution actually helps, because that limits the kind of Hamiltonians that one has to consider. And numerically, one was able to show the convergence of the BCH. And after around 50 orders, which sounds a lot, but still it is a fixed number, irrespective of the number of qubits that we considered, it converges. So how does that help? How does computing H help? So this is where another thing comes in. If the unit O has only +1 and -1 eigenvalues, I can always write it, the diagonal part of it, which is the diagonal matrix with +1s and -1s. I can write it in this way. And there is one H which satisfies this relation, which is the H that has 0 or pi wherever D has +1 or -1 respectively. So if that H can be found, I can always write D as this quantity, and then undoing whatever I have done previously, I'll get O as this H +1 cross H. So I already said that what we have computed from a gate decomposition is a version of this H, and if this H satisfies this condition, you can always get the O, from which all you have to do is find one or few of its diagonal elements, whose average gives you the quantity that from that graph will eventually lead you to the trace of the matrix, right? But there is a huge problem there, which is that this problem is that H is actually log of U. Therefore, you don't know what H you are getting, because log U is it's a function, as a function of a complex variable, has many branches. So you don't know where you are, in what branch you are sitting in. But for the examples where we constructed the unitary, broke it up into gates as well as we can, and computed the H, it turns out H works out just fine, surprisingly fine, right? So that is yet another question: why did it actually work well numerically, or is there something that we are doing wrong which is making it work so? But I don't think that is the case. And also one can show things like, compared to a random unitary, the H that we construct has certain special properties in terms of the number of terms in H and how it grows. These two lines correspond to the kind of Hamiltonians we are talking about, and this is what we are talking about with respect to a random Hamiltonian. Okay. So this is the method that we have worked out on trying and simulating the case where the DQC1 circuit produces no discord. It comes with these multiple conditions, which is, one is that the convergence of the BCH formula, we do not have a concrete proof for it, that it can be done, only numerical evidence that it can be done. And secondly, there is a part that we don't fully understand, which is about how do we end up with an H that's on the right branch of the log function that allows you to compute the diagonal elements efficiently without ending up in the wrong place, right? So these are the two caveats that are there, but it still seems to work, and there is other evidence, not just this, but in terms of the Schmidt rank of the states on which this unitary is acting on, that works. How it grows, that indicates that this is actually doable. Okay. So part of the question here is that when this Hamiltonian has only, or the unitary has only 2 eigenvalues, what is happening is that the top qubit is now actually having only 2 possible states, right? One that corresponds to the +1 eigenvalue and one that corresponds to the -1 eigenvalue. So in a sort of a trajectories picture, which you talk only about the n qubits +1, you are actually saying that there are only 2 possible paths for this computation in the case where there is no discord. And when there is discord, this number starts growing. And it can grow to 2 to the n, and it becomes uncomputable or not simulatable classically. Because I don't know how to formulate that question. I have not yet formulated that question, not formulated that question formally in that language. I thought I will mention here, given the audience that is here, it seems. So in the couple of minutes that I have left, I will just summarize the following, right? There are 2 reasons that makes our approach to classically simulating the DQC1 zero discord case work. One is that the magnitude of the normalized trace can be found from any diagonal element of O, actually averaging over a few elements of O, right? So this actually can be extended to the non-zero discord case also, provided certain conditions are met, right? For certain cases it will not work, but for small, you can go away from zero discord case a little bit, and still this argument can be made to work. There is a second argument, which is O, connecting that operator O to H directly, which does not work for any other case except this, which is a good thing, because we do not end up proving that the DQC1 complexity class reduces to P. That would be fairly spectacular, but probably not true. Don't know yet. But the point is that I just wanted to make that clear. This is not a statement that that for all cases you can do this classical simulation, but in this particular case there seems to be an efficient, or at least efficient within these constraint, these caveats, a way of simulating the DQC1 circuit, which brings us back full circle, which is to say that the zero discord DQC1 case is something that one can at least within these limitations simulate efficiently. Therefore, it kind of restores the option of using non-classical correlations like quantum discord as a quantifier of the resource that goes into into making mixed state quantum computation work. So that's really all I wanted to talk to you today about. So thank you. This is a picture of our campus at ICTS-TIFR, nice and rainy even now. So questions or comments?
Yeah, questions?
Hi, Anil. So, Anil, I've always, I've come back to this problem after many years now. So, can I just ask? To me, it seems like between CL2 and not CL2 magic, there is this kind of clear boundary which is now understood from like theoretical computer science about simulability, basically.
Right.
To me, it seems to me like the problem is that this. Whenever I think of it, I'm very confused by this because it seems to me like this is much weaker than entanglement. Right. Which basically CL2 can produce volume law entanglement. So this is much weaker than entanglement. But still somehow, if it has an element of non-simulability which comes on the phases, I'm very confused by like how to even think about this. So can I ask you from the point of view of kind of formal, if we were sitting across from our TCS colleagues, right, from a formal kind of gate set viewpoint, what is the cut here about this? What is the comment that Discord is making? Is there is there a T-gate injection simulability argument here? Has anyone made any progress in this direction, or is it just hopeless?
Not that I know of. But again, if you want to go in that direction, ultimately you have to go back to a pure state, right? So you have to really think about what is this mixed state really connected to, and what are these gates doing to that larger system, right? And is it generating entanglement there? Is it generating entanglement across the system, which eventually makes it difficult to simulate? So one of the things that comes out of this is that we find that, yes, if you could simulate the evolution of a computational basis state through this particular kind of unitary, you can actually get the the value of the trace without reference to the top qubit, right? So, but, right, if it is not a zero discord unitary, you will find that doing this process does not work, because you have to figure out what happens to every single computational basis state to get to the trace, okay? But all of them starts containing the same information when it's a zero discord unitary. So that's where the difference, right? So you have to do it only once, if I'm taking the sort of trajectory language. Otherwise, you have to do it 2 to the n times if you want to get at this information. So that's one way of thinking about it, but that's about all I have.
Any other questions now? Okay, if not, let's thank Anil.